We believe the most exciting science happens where Earth systems meet. For us, this is where ice interacts with the Earth and changes the topography, where we can use remote sensing to see a volcano grow as magma gets injected, or where we can track how human water usage, taking from our aquifers or injecting water related to the energy extraction policies, change the surface. The SMU Earth Science Department sits within Dedman College. And at SMU, this is the core college where our students are receiving a liberal arts education. We're a small department, but it's very important that we educate our graduate students, that our undergraduates are in our research labs where we're doing the best research, looking at how Earth systems interact.
The satellite and the ground-based methods, they share a lot of similarities. For example, we use similar instruments both on the ground and also on the satellite to study our environment on our planet. For satellite, we're mostly using electromagnetic waves and the gravity. Remote sensing from satellite generally can give us a more complete and synoptic picture of what we're studying over large scales really quickly and consistently. It can provide observations from places where we can't readily access when they're on the ground. Places where it's really hard to do not just any ground survey, but we can view those places from satellite.
The fact that I work at the solid intersection of the solid Earth and atmosphere means that I study waves that travel through both the solid Earth and the atmosphere. Seismoacoustics is a unique field of study because it really spans two traditional disciplines. Whenever there's a big boom, whether it's underground or in the atmosphere, it generates waves that travel out. And so we can measure those waves at long distances with seismic or infrasound sensors, and we can detect whenever a country is testing a weapon. But we can do more than that too. We can also provide insight into the yield of the explosion, which is important for understanding what the capability of a country that's testing that weapon is.
SMU was the first university that began operating seismometers in the Fort Worth Basin to study what are now known to be induced earthquakes, human-induced earthquakes. Eventually, what happens in the state of Texas is the SMU efforts, along with our University of Texas colleagues' efforts, over time, seed what becomes the Texas Seismic Network. It records earthquakes across the state, be they natural or they induced. What we learned from understanding human-induced earthquakes in the oil and gas realm has now become relevant to understanding how injection of any type changes subsurface stress. So we take what we are learning from the oil and gas industry and subsurface stress change, and now that whole area of science is becoming relevant for alternative energy sources and alternative strategies to combat climate change.
It is hard to imagine a more striking contrast than the one existing between the slow, dense, deforming lithosphere and the fast-flowing, ever-changing atmosphere. And yet, the connection between climate system and tectonic system are quite deep and subtle. Understanding and studying the natural system over a variety of timescales is one of the strengths of our science. And this breadth of timescales is really germane to geoscience. In the case of glaciers, for example, understanding how past glaciers have responded to past climate variations and the rate at which they have responded allows us to understand and better forecast how they will react and how they will respond to future changes in climate.
So when we think about ecosystem processes, this is essentially fluxes of different nutrients. We could track carbon, nitrogen, phosphorus, for example. These are the foundation and essential elements of life on Earth. And when we think about methane in particular, it's a really potent greenhouse gas. But the only other way methane can be removed from our atmosphere is through these very specific microbes called methanotrophs. And so one thing we're really interested in is studying these systems, especially in relation to anthropogenic inputs of methane. And typically we're looking at these in natural gas pipeline or abandoned orphaned wells. And these are essentially just leaking this hydrocarbon into the soils. And we have almost no understanding of how that interacts with the soil microbiome itself, whether they're incorporating that carbon, whether it's just escaping directly to the atmosphere. And so this has pretty big implications. And so when we think about these microbes, it's not just an idea of what they are or what they might be doing. It's really trying to understand the breadth of that diversity and trying to understand that functional aspects. And what I think is a pretty creative solution to exploiting various resources on Earth.
So I think what stands out about SMU's approach to earth sciences is that we're very measurement focused. Whether we're studying rocks themselves or waves through the rocks, or even the remote sensing people, we all actually make measurements. And that means that we understand something about the complexity of the real world. So what I find most exciting about listening to the planet is that, it's a very human thing. And with our instruments, we can extend one of those senses even farther and measure things that we can't hear otherwise. And so it gives us new insight into the planet.
The current generation of students are experiencing rapid technological change. This comes back to our core value of collecting primary data. We want to train our students to be able to understand multiple types of data. So in the classroom, the breadth of the student interest here can be quite broad. When I think about the frontier in earth science, I truly believe that it's at these intersections. Understanding how humans are increasing the rate of change on the planet, how we're changing how the ocean interacts with the ice, how the ocean interacts with the atmosphere. We need, even within the discipline, to expand our area of expertise and work on these problems at the intersections of the Earth's spheres.